premise that we are telling R that this is not just a mere sequence of instructions. It's a function which is composed by the same sequence of instructions. And before we start, we need to put a marker that says, look, here my function begins. And then we'll have to put a marker at the end. The marker is a left curly bracket, this one, sorry, not this one, this one. How can we get it? Probably we already discussed about this, I don't remember. Did we discuss functions already? Because, you know, sometimes I make confusion with the other subject. We didn't discuss them. Okay, very good. Oh, I remember well. So, to get the curly bracket, you should keep the key Alt-GR pressed. Alt-GR is on the right of the space bar. So you keep Alt-GR pressed and try by pressing number 7, sorry. This is one possibility. If you have a US keyboard, you have the curly bracket displayed on the keys. If none of these works, let me know, and we need to devise something else. Did you get the curly bracket or not? So who, raise your hand if you did not get it. Okay, very good. So,
I go to the web.
Okay, you go to the web and you make a cut and paste. This is perfect. Do you have a Mac? No. Your PC is a Mac?
No.
It should work with Alt-GR and 7. Are you okay? Everyone is okay to this stage? Okay. Now, what I suggest to move forward is to open a window with the code that you can see on my website. And the window is this one. If you click on suggested R code, if you go to my web page and you click on suggested R code, you get this suggested code. And I suggest that we copy and paste the instructions more or less one by one. And the first instruction is, let's copy the first 3 up to here. You need to select with the mouse, and then I right click, copy, and then I go to my file and I paste, and then we comment on it. Everybody did it? Raise your hand if you are not ready to move forward. Okay, no hands raised. So let's have a comment on these 3 instructions. This is just input of data, information. Area of the catchment, it's in square meters, so it's 1214 plus 6 zeros. And then the value for the time set is 1 hour, and we put here the value in seconds, 3600, and the number of time steps the simulation should cover, which is 8760. And be careful, this data needs to be adjusted if you run the model on another catchment or if you change the time step. One opportunity to better adjust this information is to provide the same data as arguments of the function. I prefer not to do that for a very precise reason that I'm not mentioning now in order just to keep your head clean. And if I forget to say why in the future, please remind me, okay? Basically, I wanted to keep as argument of the function only the parameter vector, and I'll tell you why. Okay, now this is quite straightforward. Let's move forward. So I switch to the website. The next instruction is this qi equal 15, and there is this further instruction which defines a conversion factor. Let me copy these 3 lines. So what is qi? qi, which I define here as equal to 15, is the first value of river flow. I mod, if you don't fix a starting value, an initial value for the river flow, starts from 0. But if you have observed the data and the first value is 15, it's better to tell IMOD to start from 15. And we will see that in the algorithm there is a condition that is posed in order to start from 15. But we need to define it. So this is Q initial. The conversion factor, in order to pass from millimeters per hour to cubic meters per second, the conversion factor is 1 divided by 1000, because millimeters needs to be transformed in meters, divided by time step, because millimeters per hours need to be transformed in seconds, times the area of the catchment, because when we have a rain that is expressed in millimeters per hours, if we want to get the volume of water over the catchment, we need to multiply the rainfall depth times the area of the catchment. So this is the conversion factor to transform millimeters per hour in cubic meters per second. And of course, the area of the catchment is in square meters. Okay. Now, the parameters. Just in order to keep the code cleaner, I prefer to assign to each element of the parameter vector par, I prefer to split the parameter vector into single variables that refer each one to one parameter. This is just for the sake of clarity, because if we give names to these variables that match the name of the parameters, I can better identify what's the meaning of each of them. In fact, you see here the following 5 lines, which I cut and paste. Basically, they define the parameters with names that are easy to recognize: Cmax, beta, alpha, K slow, and K quick. Remember, K is, the 2 Ks are the 2 constants of the linear reservoirs that are used to route the contribution to river flow. Okay, good. These are the parameters. you don't need this instruction. You may use directly the elements of the vector. It's just for the sake of clarity that I put it here. Okay, let's move forward. Now let's copy this set of initialization of variables, copy and paste, and then we comment on it. I already mentioned to you that in R we don't strictly need to define variables and vectors, and especially variables don't need to be preliminarily defined. But I mentioned to you that it's a good idea to define them because it helps to get a well-organized code, something that is easier to understand. I'm not sure that I'm defining everything here, but the most important variables and vectors are defined in this list of instructions. And the variables that I need to define, as I said, are WC. W is the storage into the catchment, C is the water stored in the non-saturated areas, and then a sequence of contribution to runoff. Let's see what I'm defining here. W equal to 0. It's W2. There will be also another W that will be introduced later on. We will see. And then storage C equal to 0, because I start from these values. And then there is W slow, just 1 second. This is W slow. Okay, perfect. W slow. What is W slow? W slow is the storage in the only one linear reservoir that is used to propagate the contribution to river flow. And in order to make clearer what I'm saying, I am projecting now the sketch of iMod. So let me go back to my website. Here and here and here. Here it is. So what is W slow? It's the storage in this reservoir. You remember that we introduced two separate mechanisms for propagating the surface runoff to the closure of the catchment. One is slow and the other one is made by a cascade of 3 reservoirs. It's quicker. Okay, so I need to define the content of these, the water content of these reservoirs at the beginning of my simulation. It could be defined at 0, but if I define it at 0, the first simulated river flow will be 0. And this is not what I want, because I mentioned to you that I want that the first simulation is equal to 15. So how can I do that? The best solution to do that, or one of the solutions, is to give to this reservoir. You could also do the same for the upper reservoirs, but this is just one. So let's get this and fix into this reservoir a storage such that when I compute the first simulation, I get from this reservoir a bottom discharge that is precisely equal to 15. How can I do that? Let's look at my code. You see, I can do that by writing that W slow, which is the storage in that unique reservoir, is equal to Qi, the first river flow that I want to simulate, divided by K's law times conversion factor. So I understand from this writing that the storage in the reservoirs it's in millimeters, and because I need to apply the conversion factor here in order to pass from river flow to storage. And if you remember how the linear reservoir is defined, if I divide the outflow by K, I get the storage. Be careful. If I look at this instruction, I understand that this code adopts as parameter K the inverse of what we are used to apply. Because here, I hope that you can see if I write here on the blackboard, storage W, let's say W0, is equated to Q0 divided by K. We used to define this relationship in a different way. We defined previously that Q is equal to W divided by K, and therefore we said that K had the dimension of a time. Here, it's the inverse. No problem, we just need to know. This is a convention and workflow that was adopted in this program that I found on the web. It's no problem at all. We just need to be aware. Of course, we can define K as a time or the inverse of a time. We just need to know. It is more convenient because if we define K as a time, usually in seconds, it's a very huge number. If we take the inverse, it's close to 0. No problem. Doesn't change anything, but we need to be aware of that. So, if we define this storage in the catchment, in the slow catchment, in this way, we are sure that in the first simulation, we will compute Q as K times W slow, and we will get exactly Qi in output. If it doesn't rain, if it rains, it may be some more, but not much different. If it rains, it will be some more because, of course, some water gets into the reservoir, but it will not be much different. Okay, let's look at the other variables. W quick is the storage in the 3 reservoirs that I placed above, and you see that it's a vector because they are 3 reservoirs, and therefore I need to take memory, to keep memory of the storage in each of them. So this is a repetition of 0 3 times. Rep REP, I think we already discussed it. It's an instruction that allows you to repeat numbers. So basically, if we go to the R console, here, if you make rep 0 3, you get 3 zeros. Good. Okay, and then there are these 2 vectors, ER1 and ER2. You may remember they are the 2 contributions to surface runoff. And these 2 contributions, basically, they are 2 vectors, and they need to be defined as vectors with length, number of time steps, and delta t. Okay, good. ER will be the sum of the 2. Again, a vector with size and delta t. E will be the vector of the actual evapotranspiration, again, with size 8760. Qt will be the simulated river flow. In this way I define most of the variables that I need. Some of them are still to be defined and we define them later. Okay, perfect. We can move forward. Yeah.
Which is the difference between year 1, 2 and year 2?
ER is the sum of year 1 plus year 2. Okay. I hope that you remember the two contributions, year 1 and year 2. They were defined in IMOD. If you don't remember them, please have a look at the theory. Okay. Okay. Let's move forward and go back to the code. And now we have to start the computation loop. Let me copy this up to this first instruction, W1 equal W2. Okay. The computation loop is the fourth cycle. It's a fourth cycle that is extended for I varying from a variable sk that I need to define to n delta t. So why I define this variable sk? To allow me to start from a time step that is different from 1. Let's fix sk equal 1, so we perform the simulation over the whole data set. This allows you to change the timing of your simulation. Okay. Now I have to use a second curly bracket to mark the beginning of the fourth cycle. Now I am defining another W. Why do I need another W? Because W is the storage into the catchment. And I need to make a difference between storage at the beginning of the time step and storage at the end of the time step. Of course, if I look at each time step, the storage at the beginning in the catchment is different from the storage at the end, because it may rain and I may have some evapotranspiration, some river flow, etc. So the storage changes. And therefore, given that I'm using a finite difference approach, I need to keep memory of storage at beginning and end. W1 is storage at the beginning, W2 is storage at end of the time step. So here basically I'm saying, let's take W1 equal to W2. Why this? Because I am in the first step of the cycle. In the first step of the cycle, what happens? It happens that W2 is 0, because I defined it as equal to 0. And then I just say here, storage at the beginning is 0 as well. Now I will compute through a series of instructions W at the end of the time step. I will add rainfall, I will subtract evapotranspiration, and river flow, therefore computing W2. At the next step of the loop, W2, which is storage at the end of the first time step, needs to become storage at the beginning of the second time step. This is why here, the first instruction that I place here is to equate W1 to W2. W2 was previously computed. W1 is the storage at the beginning of the new time step, which is equivalent to the storage W2 at the end of the previous time step. I hope it is clear. If it is not, ask me. Let's interact. This is the first program that we make together. And I am sure that once that you saw this, probably you are also able to resolve the linear reservoir, because it's much simpler. But given that this is the first exercise that we make together, let's take our time. I mean, if you don't understand something, ask me. It's absolutely not a problem. It may be that it's better for you. If I see sometimes the students are concerned because they may think that if they ask stupid questions, the teacher gets a wrong feeling. But I would say that it's also the opposite is true, at least for me. If you ask questions, I get a positive feeling, and for obvious reasons that I don't respect in detail. And I tell you, I don't get bad feeling if the questions are stupid. I'm sure that they will be not. They are not. It happens very, very rarely that the students ask trivial questions. It happens much more frequently that they don't ask good questions. So the same applies to you. So don't be concerned. There are no silly questions. Okay, now let's move forward by copying some other instructions. Let's take them one by one because I think it's much better. So let's take the first one, let's copy it, and then let's comment. What is this? This is nothing else than the relationship for computing C depending on W. W, I know it. I know it because I just fixed it here. It is 0 the first time step. It was computed in the previous time step for the other ones that follow. So, if I know W1 in this case, let's compute C1, which is defined, as you may remember, it's higher than W, it's storage in the areas that are not saturated. And this was derived by us. We derived this equation through integration. It's written in the same way as it is reported on my web pages. That's it. You also remember that we derived a second equation for deriving W depending on C. We will use it later. For now, this is what we use, and this is what we derive through integration. You remember that complicated integral we got here, precisely here. Beta, what's called beta k, and of course there is the problem that you don't see here the relationship. You see its interpretation, its algorithmic interpretation. But if you check, please take your time, check it. If you find mistakes, you have to tell me. Otherwise, please check it and get fully convinced that this is what we obtain together. Okay, this is C1. Let's move forward. C2. What is C2? C2 is the C value at the end of the time step. And it changes. At the beginning of the time step, we have a C value. At the end of the time step, we have another value. Because there is rainfall. At least there is rainfall. But also there is evapotranspiration. Now, let's make a first computation of C2, which is nothing else than C1 plus P, rainfall. And be careful. This is P, it's rainfall. We called it rain. We need to change this. Because here it's using P for rainfall. Stands for precipitation. Okay, so C1, you remember, it's water content in the non-saturated areas. We sum precipitation and we get the same water content in the non-saturated areas at the end of the time step. But we have to check that this water content doesn't exceed Cmax, because if it exceeds its maximum value, we have to put a constraint that it takes the maximum value, no more. And so this is why here you see that we are not taking C1 plus P. We are taking the minimum between C1 plus P and Cmax. Good. We still have to subtract evapotranspiration. Let's do that later. Okay? Okay, let's see the next one. Now we can compute a first contribution to runoff, which is year 1. Year 1 is given by the exceedance of rainfall with respect to Cmax, provided CT reached Cmax. So, year 1, it is the maximum value between what? Between precipitation plus C1 minus Cmax, and be careful, this difference, precipitation plus C1 minus Cmax, can be positive or negative, or 0. It is positive if precipitation plus rainfall is greater than Cmax. It becomes positive. It means that the catchment got saturated. It is negative in the opposite situation. If precipitation plus rainfall is lower than Cmax, this first contribution is negative. Negative doesn't have any physical meaning. So if it is negative, we have to put a constraint that we get a 0 from this first contribution. And in fact, what we take here is the maximum between 0 and this difference. So if the difference is negative, the max is 0. Prego.
Scusa, quando hai finito la lezione puoi lasciare
Il cavo.
il cavo per il comando?
Certo, lascio qui. Prego, grazie. Prego. Okay, so let's take the next one. W2, perfect, because this is what we guessed. I mean, we need to compute the new value of W. And this is nothing else than the relationship that we derived on the blackboard for W depending on C. Please check. So this is W2, but remember, we still need to subtract evapotranspiration. So at this stage, I am expecting that the algorithm proposes to subtract evapotranspiration. Let's check if this is true. Now, first, there is a computation of the second contribution to runoff. Sorry, made a mistake here. This is the second contribution to runoff. You remember the second contribution was Ct plus 1 minus Ct minus Wt plus 1 minus Wt. And this is precisely what's written here. With the condition, we have to make sure that it doesn't become negative. So again, we take the max between this difference and 0. Okay, now let's compute evapotranspiration finally. And let's take 3 lines and cut and paste them together. Evapotranspiration, actual evapotranspiration, needs to be computed depending on potential evapotranspiration and depending on storage into the catchment. And this is what is written there. EI, it's actual evapotranspiration, which is computed depending on storage. Here it's computed depending on C, which is directly related to storage. Doesn't matter. C or storage, they are related to each other. And then we can recognize in this line, the third one starting from the bottom, we can recognize the relationship that we introduced in the theory for computing actual evapotranspiration. Now this actual evapotranspiration needs to be subtracted from W. In fact, we see here that W2 is updated by subtracting evapotranspiration. Again with a constraint that W2 doesn't become negative. Because it may happen that when you subtract evapotranspiration from the storage into the catchment, you get to a negative value. And then if it occurs, it means that you have to put storage at 0. Negative storage doesn't have any physical meaning. Perfect. And then, last line, let's sum year 1 plus year 2 to get the total contribution to surface runoff.
In the computation of the actual evapotranspiration, what is EP, the last one?
It's potential evapotranspiration. So this is what we call evapo in our. Okay, so we need to change this name as well. Okay, let's quickly get to the end of the loop. And let me copy all the instruction to the end of the loop. One second. Here we are. So, we are here. Sorry, just 1 second. Okay, we are here. Now, we have ER computed. ER is